For the past decade, there's a revolution happening in high-performance computing. There's a figurative explosion of architectures that we can use. However, using those architectures efficiently requires intimate knowledge of the hardware's details, and sometimes it even requires completely redesigning an application just to follow certain programming paradigms. This is starting to become a major problem for maintainability, and in general, is becoming an obstacle in advancing scientific computing. In this talk, we will present Dace, a data-centric programming workflow designed to address this issue. Dace is the work of the many people you can see here on the slide at the Scalable Parallel Computing Lab at ETH Zurich and other collaborators. The core concept in Dace is an intermediate representation called Stateful DataFlow multigraphs. And this representation can concisely represent and optimize a wide variety of programs and map their code to CPUs, GPUs, and FPGAs efficiently, all from the same source code. Let's begin. Okay, so first, as most of you already know, the compute architectures are becoming faster in terms of computation, but data movement remains expensive. This is obviously a limitation given to us by physics, but this is so extreme nowadays that multiplying two numbers is 3 orders of magnitude cheaper than moving those two numbers into the processor to multiply. Of course, this problem becomes much worse when we go to distributed architectures where the problem increases exponentially. And to top it all off, we have different customized processing units, for instance, tensor cores within NVIDIA GPUs or TPUs, and even processors on peripherals like network cards and reconfigurable architectures such as FPGAs. So this is becoming a major problem. This is becoming a major problem also from the software engineering perspective, where the once omnipotent computational scientist who could write the entire program and run that, now instead, 2 roles are emerging in many computational sciences, and this also includes deep learning, but a lot in scientific computing. And what we're seeing is that those 2 roles are the main scientists who know what to compute, and the performance engineers who know how to compute it efficiently. Now, unfortunately, the 2 roles are acting on the same code for most of the time, and this is becoming a real problem for maintainability. So, for instance, when a new hardware architecture comes out, a performance engineer must massage their code and really sometimes do a complete rewrite in order to fit a hardware architecture, even if it's just a new model from the same company. And so even switching between 2 different kinds of GPUs can be very cumbersome in terms of development effort. And on the other side, since this goes both ways, the domain scientists, they at some point get to a point where they cannot understand the code that they're processing because of all of the optimizations. So the use of libraries like MPI and CUDA and other programming languages, multiple programming languages in the same environment, basically make the code a lot more bloated, and it's really hard to find where the actual computation sometimes takes place. So if we look at the performance engineer and what their role is today of a performance engineer for a given application, we see that no matter the hardware architecture we're looking at, whether it's multi-core CPUs with the vectorization optimizations and optimizations for high cache utilization, or whether we're looking at GPUs where we want to minimize warp divergence, and even FPGAs when we want to really optimize the number of round trips that we have between the actual circuit and the external DRAM, which leads to interesting circuit design patterns like systolic arrays and pipelining in a more general term. As you can see, none of these optimizations actually have anything to do with the computation itself. You can even claim that high performance optimization mostly nowadays is all about optimizing the data movement. And if you could take these 2 problems, the fact that we have all of the optimizations being around data flow and the fact that we have these 2 roles that exist, I mean, we cannot deny that they exist, how can we design maybe a different programming workflow that can support both of these at the same time? And so this is how we ended up with the data-centric programming model. It's something we've been working on at SPCL at ETH Zurich for a while. There are a lot of contributors to this project, some of whom I mentioned in the title slide, but there are many more. And so the idea behind this kind of interface is that it starts at the most basic level, separation of concerns, even at the basic programming phase, where we have two sets of files or two sets of codes that we want to work with. So a domain scientist, they work with the input code, right? We talked about what to compute. So we can use different front ends in different programming languages like Python, TensorFlow, other domain-specific languages fall into place here. For instance, for other deep learning frameworks. And this goes into a basically scientific front end that builds an intermediate representation for the performance engineer to work on. Now, as opposed to other intermediate representations that you may know from, let's say, compiler analysis, what we think is the right approach, at least with this representation, is that we try to promote a completely white box approach. So as opposed to intermediate representations that are part of compilers that you write passes, optimization passes, and then they may run or may not run. But as a performance engineer, sometimes you have no idea why they're not running, and you would have to really try to adapt your code such that it works. Here we show exactly the representation of the program as basically revolving around data movement. So I'll talk about this in a bit. We call this data-centric representation stateful DataFlow multigraphs. And as you can see this representation, you can see all the optimizations that you can perform, and they are expressed as graph transformations. So either programmatic transformations that you implement or just manual manipulation of the graph. And all that without changing the original source code. And then subsequently, a performance engineer can then try to map it into a system. And our Dace framework supports CPUs, GPUs, FPGAs, and you can inspect the performance via instrumentation and other tools. And with that, keep optimizing in a closed feedback loop. Now, about maintainability, the reason why we have these two separate code bases is that the domain scientists can still see their original code as the scientific computations, while the manipulations to this intermediate representation are stored as deltas. So in that sense, we maintain the maintainability by having the performance engineer save the original graph plus all the transformations, and then the domain scientist can even modify their input code, and as long as these deltas still apply, as long as these transformations still apply, they would still keep having the same performance, more or less. And if a new hardware comes out, the performance engineer could just branch out from the deltas and try to manually tune or optimize the SDFGs for a different platform. And so with that, maybe I should talk about the intermediate representation in a bit more detail. So we base our intermediate representation on concepts from data flow programming from the late 70s and the 80s, where basically if we have a computation like we have here, the x squared plus sine of x over pi, let's put it in a box. Okay, so in order to compute this expression, what we need is to get x from somewhere, and we denote the memory regions as circular nodes here in this kind of graph, and we output y somewhere else. From this point on, we close this box. We call them tasklets. They can be at any granularity you want. So the obvious tendency is towards finer grained tasklets because they are not allowed to have any kind of side effects. They just receive the information and pass on a different set of information to the other nodes. And from this point on, they're completely opaque, and we don't look into them for the entire purpose of the transformations. The memory movement units, so these small regions that we're passing, we call memlets. And so this is the basic kind of representation where we have a data flow where the nodes are having data flowing between them through edges. Now, if we want to express parallelism in this representation, let's say we can name these memory regions by putting names on the nodes themselves. You can see that parallelism is expressed very natively. And it's very intuitive to say that two things that are executed in parallel are actually parallel in the graph. But then there is a real problem also in other data flow representations is when we have really large graphs, and even just multiplying two matrices of 200 by 200, this becomes infeasible to represent as a explicit graph. And this becomes obviously impossible to represent for problems that we don't know the sizes in advance. So this graph that you see here becomes a parametric graph. And in order to deal with that, what we do is we use the fact that a lot of applications today are composed of repeating subunits of those tasklets. And then we can basically group them into some scope, as denoted here by this trapezoidal region, parallel scope, which is parametric, which we call a map scope. And within those two trapezoidal nodes, or more formally, the subgraph that is dominated by this node here and post-dominated by this node represents something that will be replicated for the amount of times that is written in the integer set on this node here. Now, as a programmer, you don't need to do a lot by just, besides just defining that this is a parallel scope. And when you specify a memlet like this, A at I, we have a symbolic math engine that we employ in the Dace framework that propagates the axes through the map range, and then essentially this memlet here is generated automatically. Now, why this is important? I mean, right now it doesn't seem too important because it's very clear what's being accessed. But sometimes, as we see in other applications, let's say we're manipulating a matrix, but we're only working on a single column of that, then it's very important to know that exactly we want to work on that column so that we don't copy extra data. For instance, if we're working on another, let's say, coprocessor. So this is the basic of the data flow itself. This is an acyclic multigraph. But then there's another problem. So the other problem is, let's say we have these two graphs here in parallel. So they are one next to each other. The two connected components will run simultaneously. And so this now creates a data race that we want to resolve. So how can we say that, let's say, the computation here on the left comes before the computation on the right? So we nest those acyclic data flow graphs with another directed graph, which represents a state machine. And as you can see here, those blue edges here, they are state transitions. So they have assignments and conditions that they can have on top of them. And this acts exactly as a state machine. And so you can represent very concisely, for instance, loops, as evident here by this solver that runs some very simple stencil until iteration capital T. And as you can see, most of this graph is parametric and symbolic. And these T, H, and W can even be specified at runtime. And this graph can still be transformed even though we don't know anything about the actual sizes. So the representation itself is a language. And there is more to it than these four elements that we've seen so far, the states, tasklets, arrays, and maps. We also have, for instance, nested control flow in data flow, so we can nest SDFGs within SDFGs. We have streams that act as FIFO queues, and we have the counterpart of maps to streams, so basically a scope that creates a producer-consumer relationship. And what happens when we have more than one tasklet writing to the same memory location, then we can define conflict resolution edges that have an operation between them. So essentially covering all the read, modify, write atomics, but even more. So that, and also lastly, the library nodes, which can interface with existing implementations, so that if you have a really well optimized intrinsic implementation, you can just use that node instead. This also contributes to optimizing very specific patterns in like domain-specific transformations. And so overall, this is the entire representation, not much more to it. We can represent with it many applications from many domains. And here we can see, for instance, a database query. So we can see here how the data flows from in parallel to some tasklet that maybe asks whether the value in A at I is smaller than 0, and if so, pushes it to the stream here. The stream is directly connected to another array. So in essence, this would write it to the memory at B. And if, of course, this passes the filter, we want to know how many elements we filtered. So we have here an array of size 1, B size, where we just write 1 to it within the testlet, and then it gets, with the conflict resolution, it becomes maybe an atomic operation or other operations depending on the target architecture. So we have full operational semantics in the Supercomputing 19 paper. You can take a look at that if you're interested. I'm not going to go into that level of detail. But in general, this is a representation that can, represent a lot of applications in parametric graphs, but I didn't mention so far why it is useful for heterogeneity. So one of the main concepts that we can use this for, now that we have these parallel scopes, is to introduce hierarchical parallelism, for instance. So we can put a map in a map, right? So we have a few more annotations on the nodes, not just the fact that they're a map, but also their schedule. So this is scheduled to a CPU multi-core. So that's basically an extensible enumeration. So you can implement your own targets, your own schedulers. And the arrays here have storage locations. So we know that this array is stored on, let's say, the CPU heap. And as you can see here, we specify some squaring operation in the testlet, see the memory flowing here from A to the testlet, and we can see that, well, depending on the size of TN, depending on the cache line size, we won't necessarily have optimal performance when we work with such a tiny scheme. So one way to optimize this is to introduce a local array per core. Right? So in a standard application, I would add an array. Here in this graph representation, I can transform the graph by just adding an array in between. And as you can see, we can really use the memlets to see the extents of the array, to see the addresses that are necessary to go and copy the memory here, and even offset the other addresses here going forward. So it's a really easy way to manipulate code in terms of data flow without modifying the actual computation. The way we generate code from this is actually very straightforward. So here is, let's say, a piece of the generated code that this graph represents. And if we have a CPU scheduler, we use OpenMP to generate a loop. Obviously, this could be implemented in any other framework, but we chose OpenMP because it's really easy to use. The path of memlets going from A to TA is represented by another operation. So here we have, of course, a local memory definition and a very efficient copy operation. And we implement copies from different pairs of storage locations. And the internal map here, this basically single core map, there is no parallelism in it. So we just implement it as a for loop. And the important thing to remember here is that we never change the tasklet code. So the tasklets here, we convert them into C++ code, and that's it. So this is pretty much the end of the process for these tasklets. And as I will show, this leads to very high performance in terms of the resulting code after transformations. So it really doesn't matter what the tasklet is. And so I think that this is one of the strengths of the data-centric programming model. So now, let's say instead of CPUs, I want to run it on a GPU. Right? So this would normally incur a complete rewrite of the code, like having CUDA and creating a kernel. And so for us, looking at this graph, all we have to do is to run another transformation. So actually, this is an existing transformation in our framework written in Python. And this is called GPU transform. So essentially, all it does is just adds an array here in between, such that the memory is on the GPU global memory. This, of course, incurs a copy on this edge here and changes the map schedule here to GPU device. This one automatically changes to GPU thread block. So you can see exactly how this completely translates the code. This helps us to make really drastic changes in a very easy way or intuitive way. And so just to tell you, this transformation, if I remember correctly, is written in 260 lines of Python code. So also it's very easy to write such transformations, which is another boost for productivity, in my opinion. And so to give a bit more detail about how we generate code to these load store architectures, CPUs, GPUs, and likes, we chose to generate, as you can see here, C++ code, or mostly C code. So we try to keep the code simple in terms of the generated code. And the reason why we chose that instead of, let's say, LLVMIR is because the support for compilers on different architectures is much wider. So supporting Power 9 CPUs, as we have for another application, was pretty much out of the box. We can support, the IBM compiler. We can support ICC, other compilers, CUDA, and we generate HIP code for AMD. So we also support the GPU, like both GPU device types. And in general, how we generate the code from these state machines is that we have construct detections for loops, for while loops, for branches. And in the worst case, we fall back to gotos, but that happens rarely. So there's that. And we can exploit a lot of parallelism when we have these data flow graphs. So when we have obviously a map scope like you've seen before, then it can translate into an OpenMP scope. When we have conflict resolution, we use atomics, use separate threads for the consumer-producer relationship. On GPUs, we can take the separate components and actually run them as different GPU streams. And so as I shall show, this actually yields an interesting performance benefit, especially in more complicated applications where you have a lot of kernels happening all at the same time. And when we have copies between different devices, whether it's CPU to GPU or a collaborative copy between GPU global memory and GPU shared memory, this is all represented by the same construct, which is just a path of edges between one array node and another array node, or one array node and a tasklet. And so simple representation that can cover a wide variety of patterns. And when we want to map to reconfigurable hardware, like FPGAs, so this is something that would seem completely different. I mean, now we have to program circuits instead of a set of code. And in that, we actually generate two different backends. So we support both of the big FPGA vendors. So we generate a high-level synthesis C++ for Xilinx, and we generate OpenCL for Intel FPGAs. And the degree of things that we can exploit in reconfigurable hardware is the same, if not larger, than what we can do with CPUs and GPUs, the load store architectures. Basically, if we have parallelism, we can exploit spatial locality and introduce replication. So what you see here on the right-hand side is a very concise representation of a systolic array, where basically we have a processing element. That processing element gets replicated p times, and now we can communicate through streams between the different parts of this circuit. So we can see here how we read once from DRAM and then go through all of these processing elements and in a pipeline fashion. So this yields very high performance as well on these hardware architectures. And on the domain scientist side, so we have, as I said, a lot of front ends, but the main front end that we use is Python. And so the programs, they can integrate in existing Python code. So similar to what Numba does, we put a decorator on top of a function, and you can work with NumPy code. So we support a lot of NumPy, but not all of NumPy, and we don't support list comprehensions and dictionaries and all the quirks of Python that you could use. But then we can convert most of these codes into SDFGs, and this is something that you can then work with and transform further. So even if the original code was not really the best code, then we can keep working with that. And if you want to be very explicit about your data flow, we can even use this bottom here representation, which is just, let's say, a textual representation of the SDFG. You can really see here how we have a program. We can even combine the two. So you can have a map, and you can see exactly the memlets here coming in, coming out. This is a transposition operation, but you can see here how this is separate computations from the data movement. And in the end, what we do is we compile an SO file or just a library file for each platform. And we also auto-generate an include file. So this can be linked from, this has a C ABI, so you can link from it from Fortran or C. But if you run it from Python, we also load that library at runtime, and we can invoke that function. So all in all, something that we can use out of the box and integrate into other programs. And so just to talk a bit more about transformations, let's say we wrote a matrix multiplication that, let's say for some sizes of matrices, this is actually efficient. So this MapReduce approach, where we have A and V here read, and each pair of A, IK, and BKJ is multiplied and stored into this three-dimensional buffer, which is then flattened. So for very large values of K and smaller M and Ns, this is actually something that might be useful. But in most cases, it is not. So as a performance engineer, you can see this and obviously say, oh, wait, temp is not used anywhere else here. And there is a direct path here from this task that's going through temp and the reduction to C. So why not replace that with, let's say, a bit more classical representation of matrix multiplication, which is, let's say, the three-dimensional loop with the addition directly to C. So this is another data-centric transformation. And the way that the transformation looks, so it's called MapReduce fusion, and the way that it looks inside our code is basically we look for a subgraph pattern, and this is something you define. So you define your subgraph, which is here like say a map exit node, an array, another reduction library node. And then we have two more functions, one for, let's say, manual matching if you have your own conditions, so you can write this in Python yourself. And the replacement function, which just uses Graph API to remove and add nodes or edges or whatever as necessary. So this constitutes a whole transformation. And what we do is we encourage also, we have a set of 20 such, I think 20-something transformations built into the system as like a standard library of transformations. But we encourage performance engineers to write their own transformations and can apply them, in a more programmatic way for their own applications. I mean, if there are domain-specific transformations to be applied. So in our paper, we address more challenges. So for instance, what happens when we work with the sparse structures, or what happens when we have the nested state machines, so what I mentioned before with the nesting of SDFGs. I'm not going to go into that level of detail. What I am going to go into is what it looks like for the performance engineer to work with such a representation. So as I said, we try to work with, or try to create a different workflow. And in that workflow, we can obviously have the regular IDE used for the development of the front end, right? The high level code. But once we go into performance engineer mode, we want to see the code, but also manipulate the graph. So we have a live view of a graph that we can basically mutate and change directly. We can click a node. You can see here all the properties of that node or the edge, and you can modify them. You can see all the existing transformations, and you can see the generated code. So if you're interested to see what really happens from that representation, you can inspect it yourself. And those deltas that I mentioned before are saved as part of the SDFG. So you see them as a history that you can undo, revert. And so this is what's called diode. So a data-centric integrated optimization development environment for shorts, I guess, diode. And we also have a work in progress, but also public. So we have on the Visual Studio Code store, we have a plugin that we're working on for VS Code, within VS Code. So you can see here how we can inspect the graph live, and you can zoom in, and you can even, if you zoom in enough, you can see the actual code, you can jump to the source code directly, apply the transformation, see the history. And so we're really trying to understand what would be the best kind of workflow for both roles to work in parallel. But this is really something that is open research at this point. And so as we apply those transformations, so let's say we take this matrix multiplication from before as an example, you can see here, for instance, the matrix multiplication that had the reduce node and the big temporary buffer. So that doesn't even scale beyond 1024 cubed because of the sheer size of that temp array. And at some point, we just can't fit it in. But as we apply MapReduce fusion, it's a bit faster. And the memory footprint reduces drastically, and we can apply more and more transformations, some of them manual. Not every transformation is necessarily going to be better than the previous one. I mean, we cannot just apply a greedy approach to optimization, but this is why we try to promote this white box approach. I mean, we are aware that this is exactly what happens. As a performance engineer myself, not every optimization, is going to make it faster, but it could be a stepping stone for a better transformation. And you can keep optimizing this. And basically after 6 clicks of a button on the diode interface, you can get to some implementation that is actually 75% of Intel MKL, which is not too bad for like a 7-line Python code and 6 clicks. But this only uses the default parameters for the transformations. So for instance, tile sizes and such. If you auto-tune the transformation parameters, you can actually get to 98.6% of MKL. And the only difference that we've observed between our implementation and MKL was prefetching operations, which are also a data-centric transformation that some people are welcome to implement. And so even that final leg, we believe, can be made with higher level code. So We tried this Dace framework on a variety of architectures. We tried multi-core CPUs, we tried the GPUs of various kinds, we tried the FPGAs, and we tried this SDFG representation versus general purpose compilers and polyhedral optimizers, and even the best of the best state-of-the-art frameworks and libraries. And when we try to compete with them, so we try to look at fundamental computational kernels. So the matrix multiplication that we've seen before, but other like database query that we've also seen, histograms, stencils, and sparse matrix vector multiplication. And in this plot here, you can see that we're here on the left and lower is better. You can see that obviously this 98.6% of MKL is something we attain. We can observe and find more transformations that the other compilers, including ICC, cannot find in query. And this is thanks to this data-centric representation that can also see things like the FIFO queues as a first-class citizen of the representation. And we see similar results in all of the other programs, and especially in sparse matrix vector multiplication, we can see that basically our representation is on par with MKL, getting the same performance. And we see a similar picture with GPUs and FPGAs, where we get here 90% of Cutlass. Cutlass is like a cuBLA, so it's a linear algebra library, but written within CUDA. So we consider this, because this is written by NVIDIA, we consider this to be the, let's say, best attainable performance on GPUs for matrix multiplication. And our performance ranges between, I think it was 90% and 105% of Cutlass, depending on sizes and parameters. So you can attain pretty much the same performance. But even if we get 90%, I mean, for some cases, this is exactly what you need because we have full control over the representation. For FPGAs, the performance is even better. So we have a really good performance even compared with languages that are meant to work with FPGAs, like Spatial, for instance, we're 20 times faster in matrix multiplication. But really what you can see here is compared with high-level synthesis, which is just standard C code, we consistently outperform those kind of representations, which, again, this representation was designed with data flow and state machines in mind. So it is already a much more promising, let's say, basic representation to work with reprogrammable circuits. And just to show you what the fully optimized matrix multiplication application looks like. So if we really want to see, like, this is the GPU matrix multiplication, if I could zoom in, I hope this works. You can really see how A is copied to the GPU. We can see a tile size here. We applied the transformation called double buffering, which can read from the global memory to the shared memory while processing on another slice of the shared memory. So all in all, I mean, this is just a couple of transformations, not too deep of a search, let's say, space. And the task here is still C equals A times B. The conflict resolution edge here is still addition. Nothing changed from the previous representation that you saw before. But still, this is a very flexible representation that you can, let's say, put more computations into or do other things, and completely open. And so we were still not convinced, so we looked at other applications. So this is a benchmark for polyhedral applications called Polybench. It has 30 applications. Here we try to see what happens when we don't perform any kind of transformations, just to see the power of the representation itself. And we see that in most cases, we are on par with the polyhedral compilers, not in all cases, but that's fine. There were no transformations involved. But in GPUs and FPGAs, the performance is also more interesting, because when we compare this representation with PPCG, which is a tool that is specifically designed to take polyhedral CPU code and turn it into GPU code, our GPU transformation, the one that I mentioned before, can sometimes achieve up to 12 times performance speed up over the other implementation. And the reason why is what I mentioned in the beginning. The fact that we have a symbolic math engine and the fact that we know when to copy and what exactly to copy is the reason why we can gain more performance. And if you look at the FPGA part, I mean, you can see that oddly enough, there are no other bars but ours. But this is intended, so no worries. The reason why is that this was the first time that someone was able to synthesize, place and route, and even run to completion without hanging the entire Polybench dataset on FPGAs. So again, we seem to think that this is a very promising approach for handling all the different kind of architectures without changing the code too much. And so we were still not convinced, so we tried a bit more complicated applications. So one other kernel that we tried was a breadth-first search. So this is a completely irregular application. We compared here with the state-of-the-art libraries, Galois and Gluon for CPUs, Gunrock and Grout for GPUs. And what we can see here is that when we tried different kinds of graphs, we tried roadmaps, social networks, and synthetic power law graphs, we are with the CPU on par and sometimes a bit faster than these other implementations, which were manually optimized for, I think, nearly a decade. And for GPUs, we also see that we can, depending on the graph type and depending on the transformation scheme, we can outperform the state-of-the-art libraries in all of those cases. And just to show you a bit about the CPU representation, so what you see here is the fully transformed CPU graph. And in my opinion, I think that you can apply more transformations. So only 3 transformations were applied here. So with more transformations for other graph types, I think we can reach the same performance or higher than the other libraries. And you can see that it's still more or less legible. I mean, we applied here map tiling and a few accumulation transformations. But all in all, I would say that this is a pretty promising approach that changes the workflow from the beginning and has this intermediate representation that is based on concepts from Dataflow. It can apply to a wide variety of applications. So there are more applications that I'm not showing here. For instance, we have applications in deep learning, in numerical weather prediction, and in quantum transport simulation, which I actually have a bit of time, so I'll show. And in all of those applications, we can achieve state-of-the-art performance with this representation. So all in all, I think that this is a very promising approach. And since it's fully written in Python and generates C code and compiles with CMake, we can just pip install this Dace project. It installs all the dependencies on its own, and you can try it and download it and let us know what you think.